Hello, and thanks for watching today's class on AI images. I'm Eric Salvaggio, your regular lecturer. In our previous session together, we talked about the early history of AI up to about the 1980s. And we'll pick up a bit of that history in this talk today and help think through the factors that got us to where we are now. An essential part of that story is the World Wide Web and the massive amounts of data that soon became available for building these AI systems. But before that, we're going to take a little bit of a look deeper at AI systems in the 1980s. By cultural standards, AI in the 1980s was probably less exciting for the art world. Development of AI was situated mostly in industry and dedicated primarily to something called expert systems. At the time, artificial intelligence work was all about taking the things people did for work, breaking them down into a series of steps that a computer could follow. This is one example from Beverly and William Thompson in 1985 of a cardboard inference engine, a series of note cards that you might create from a conversation with a botanist. Once you had these note cards, you could code this sort of if-then program into a language called Pascal. So here you see if class is gymnosperm and leaf shape is scale-like, then family is cypress. Right? So that's the rules that they're following, and you can do this through note cards. And then you sort of have to figure out how to tell this to a computer so that it can do the same sort of decision making. It was in the 1990s that an anthropologist named Diana Forsyth went into these computer companies and universities to study the people who were doing this work, then considered artificial intelligence systems. These people were called knowledge engineers. And Forsyth went to these labs and observed, asked questions, and reported on what she saw. At first, she was struck by the comparisons of what these knowledge engineers did and what anthropologists do. Anthropologists go into places that they aren't familiar with, and they observe, they take notes, they write about what they see. So did these knowledge workers who were doing research on AI. They'd go into offices or factories. They'd look at decisions that workers were making, and they would take notes on what they saw. Anthropologists write books, and knowledge engineers write software. The difference, Forsyth wrote, was that the anthropologist is chiefly concerned with culture, while the engineers were chiefly concerned with actions, observable actions. The values and assumptions shared within a group constitute part of what anthropologists call culture. Culture defines what we take for granted, including explicit formal truths of the sort embodied in scientific paradigms, the tacit values and assumptions that underlie formal theories, and the common sense truths that everybody knows within a given setting or type of setting. Our cultural background influences the way in which we make sense of particular situations, as well as the actions perceived as possible and meaningful in any given situation. That's from Forsyth in 1993. Forsyth observed the ways that culture emerged through how these engineers approached their work. If they were trying to write a computer program based on watching what professionals did, they would observe these professionals first. These AI researchers had the idea that they could model human expertise by studying it and breaking it down into steps or procedures. And once you had these steps, you could write a program that would follow those steps as a set of coded instructions. Then the program could apply these steps and you'd have automated the worker's actions. This is a way of thinking about problems that's very specifically focused on translating the actions of humans into something useful to a particular piece of technology, the computer. But to do that, people had to really say what they were doing. They had to be able to explain things in ways that could be turned into steps. And these intuitive practices, cultural practices, were challenging to explain it that way. The engineers rarely asked why the rules that they were observed were being followed, and they weren't looking at how they might be done differently. They simply wanted to move something they saw into a language that machines could understand and follow. And in a sense, they were aiming to remove culture from what they saw, because machines don't understand context, they don't understand culture. Machines understand steps and instructions. So AI development at this time was kind of spooked by culture, because culture couldn't really be broken down into these procedures that a computer is trying to understand. And Forsyth wrote in her paper that this became its own kind of culture. You might imagine in this culture that creativity is a frustration, because if an expert tackled a problem in a different way every day, that's going to pose a real challenge in writing this set of steps and commands that a machine can follow consistently. So for this reason, and for a bunch of technical constraints, AI in the 1980s is focused on work that tends to be repetitive, tends to follow sequential steps to reach a goal. Basically, if-then statements. If this condition is met, do this. If not, move to the next question. The idea of asking an AI to make something really new, like an artwork or a painting, it was just too far off the radar. It's too challenging to describe that process of creativity as a series of steps. Soon, though, the world of engineering and culture would fuse together once again in the development of the World Wide Web.
It spans the globe like a superhighway. It is called Internet. The net to longtime users.
Internet is a whole group of networks.
The net is made up of some 12,000 individual computer networks. Internet began back in 1969. It was a tool of the Pentagon. But nowadays, just about anyone with a computer and a modem can join in, usually for a nominal fee.
When Carol Phillips wants to know what's going on in her community, she takes a walk to the computer in her family room.
Critics say one danger is this could turn out to be an elitist system, one available only to people with a computer and a modem.
Phillips connects to Cupertino, California's city-run network, CityNet.
An effort to harness the information explosion, to allow the high-tech flow of facts and figures between government, business, schools, and citizens. Computers, databases, and consumer electronics, designed to put vast amounts of information at users' fingertips.
One of its greatest achievements appears to be as an aid in scientific research. By tapping into Internet, a scientist can share knowledge with another scientist at lightning speed.
And thus widening the gap between the haves and the have-nots.
Internet keeps growing, adding users and services.
Promoting the information superhighway, Vice President Gore on Wednesday said he could foresee the day when a youngster just home from school, given a choice between Nintendo and the Encyclopedia Britannica, would choose to access the encyclopedia. If that is so, that might be even a greater accomplishment than the technology.
Here you have a picture of the first computer used to build the World Wide Web. This is the first server, which sat on Tim Berners-Lee's desk at CERN in 1990. And I'm gleeful to point out that it has a note telling people not to turn it off. You can imagine that today there's probably no single button you could use to turn off the internet, but it's quite wild to think that at one point there was. Of course, as soon as it connected to another computer, that other computer would take over. And so this is what a network is, right? The more computers you have, the more reliable the network is, the bigger it is. In the video we just saw, you heard this often repeated description of the World Wide Web as vast amounts of information at our fingertips. When the web emerged, there were a lot of utopian dreams about what was going to be possible and how to prepare the world for that transformation. So let's think for a minute about all the things that happened to make the web possible. Computers were more common, they were more affordable, they could fit on a desk instead of filling up a room. You could connect these small machines to other small machines and create new, extremely powerful networks of machines. All these connections allowed people to communicate and make decisions in real time in a way that would have been very hard to do before. And in 1996, for the first time in human history, storing information on a computer became cheaper than storing it on paper. And that keeps going down. So now more people are digitizing more information. They're looking for ways to store it and to make it more accessible. And in Silicon Valley, there's a movement afoot that saw the World Wide Web as reshuffling existing power structures. They would distribute real-time decision-making, and people would be free to coordinate themselves. It was going to change politics. It was going to change the media. And we're going to watch a clip that explains some of this thinking. And it also introduces an early experiment at a conference where attendees were given a kind of image sensor device. So let's watch what happens. I want to point out something here, which is that everyone's acting of their own free will, and it's coming together in this collective play of the video game. And we heard about the World Wide Web going to create a sort of super organism or a super consciousness, global consciousness. Suddenly, this idea about neural nets becomes relevant again, not because we are building neural nets into computers, but because the World Wide Web is a way of collecting intelligence where each person in the system is making decisions and reacting to information, often in real time. If you remember the neural net idea, there's a certain variety comes in, certain variable comes into the system, and then it makes a decision, right? So rather than building a neural network inside a machine, the web is using human beings to process information for the sake of delivering more information to more people. So basically, we are all the neurons in this global machine. We are all the decision makers. And instead of building a device that does what humans do, now humans are the intelligence of the network, the global machine called the internet. So you see a rise in companies that are trying to get people to create content, to tell stories about themselves, to post photos, to share news and observations, and to basically bring this network to this constant churn of content. But all this information flow needs to be structured. And there's a lot of power and responsibility there. So in one sense, power starts moving from things like traditional media outlets. Remember, there's just a handful of TV channels in people's homes. Instead, people make and share content, and companies build the infrastructure in order for us to create that content. And they can make money off of that infrastructure. There was a huge fight over who controlled access to the World Wide Web. It's hard to believe now, but companies engaged in all kinds of illegal behaviors in order to have the most used web browser. At one point, Microsoft's Explorer, if you went to a competing browser, Microsoft Explorer would actually render their competition's web pages into gibberish, right? It just wouldn't work. And Explorer was built into your system when you got it. So this was short-lived, but there was antitrust lawsuits, and there was a browser wars, which you could go and look up and read about if you're interested. Over a few years, power started getting concentrated into the hands of a few big companies. Google, being one of the first big ones, joined Microsoft, which was already powerful. By 2005, you have Facebook on the scene, and a lot of these companies are really driven by the idea that if you give users space to create content, in exchange, they will collect data and use that data for advertising and marketing purposes. So we start to hear this phrase, which has been around since the 1980s, of big data. These companies saw massive amounts of information moving through their networks. They could use that data for marketing, but also to power up those networks, to make decisions about what to show to who, to understand business side stuff like where to increase server capacity, how to streamline their site infrastructure, find out what people were using and not using. By 2010, Eric Schmidt, then CEO of Google, claimed that humanity was producing as much information every 2 days as the human species had created up to 2003. And this pace continues. 30 years of video content are uploaded to YouTube every day. So what I'm getting at is this is a lot of data. There's a lot of information in that data, but nobody is going to spend 90 years of their life categorizing a weekend of YouTube videos. So increasingly, we've turned to machines to do that for us. We've also consistently been relying on people. The more data we have, the easier it is for us to build machines to learn from that data, to find patterns in that data, and tell us something about that data. And today, that's increasingly come to drive the types of things we define as artificial intelligence. IBM, artificial intelligence is a field which combines computer science and robust data sets to enable problem solving. Google says artificial intelligence is a field of science concerned with building computers and machines that can reason, learn, and act in such a way that would normally require human intelligence or that involves data whose scales exceeds what humans can analyze. Meta, parent of Facebook and Instagram, writes that AI is an evolving field of computer science that's already part of daily life for billions of people around the world. It can take single tasks that are tedious and time-consuming for humans and then scale them up to benefit more people in more places. In other words, each of these companies is defining artificial intelligence with regard to their own business strengths, all centered around the collection of data, analysis, and information. Automation. You have robust data sets from IBM. Google talks about this idea of data at the scale beyond what a human could look at and think through. Whereas Meta is talking about scaling up these benefits for more people to access them. The benefits of data. As companies gathered more and more data, sorting that learning from the information became the predominant challenge. The movement for AI starts to shift from business automation to automated data analysis. Think about it this way. You have enough data coming through your servers that it would take a human being 30 years to look at all of it. Much longer to analyze, to find patterns or make sense of that data. So engineers use what data they have and they start looking at small samples of it. They break it up to find patterns. And the idea is they can encode these patterns into sets of rules to follow to label and categorize the information that comes in. So you may not be able to look at all the data and find the patterns, but you might be able to say, I'm going to look at a small piece, a small chunk of that data, find patterns in that, and then extrapolate that outward to everything that comes in. And if something changes in the data that's coming in, then maybe we have an algorithm that can say, well, if that's happening, that means X, right? So you find relationships in small pieces of the data, and then you try to extrapolate that to all of the data. Now, that initial step of identifying patterns in these small sort of subsections of the data is being done by people. There is a whole industry of what is called click workers, or sometimes called ghost work, where people are paid pennies for these very small tasks, such as looking at an image and identifying whether it's a puppy or a kitten. This stuff, it's so low paying, it tends to be shipped off to developing countries. But this stuff is also done by you and me for free. When you upload a picture of a puppy to Instagram or Facebook, you might tag it as a dog. And then the image becomes part of the data that Meta can use to identify puppies. If you've ever solved a CAPTCHA where it asks you to identify 3 pictures of bicycles in a grid to quote unquote confirm that you are human, that's giving verification information to a company about what's in that picture. That's saying, yes, this is a bicycle. And that's information that they can use to train AI. Anytime you give information about yourself, you are theoretically contributing to the construction of an artificial intelligence data set. We're going to talk about that more in the future. But there's also this idea of the ghost work side of things. And Mary Gray is an expert in this field who wrote the book on the field. And so I'm going to defer to Mary Gray. Let's watch.
I got into this research by accident. I wanted to understand how computer scientists and engineers built artificial intelligence. I didn't really understand how it worked. They would often tell me, oh, we also have to hire people to label certain images or to clean up training data. And so when I asked them, so who are the people that you hire to do this work? Some engineers say, I don't really know, but I'm afraid to find out. And I was just so taken by their discomfort in the potential abuses of this form of work. We coined the word ghost work to get at really 2 layers of this new world of work. One, it's work that can be hidden from a consumer that otherwise thinks automation is doing the job. But there's another layer of meaning behind the term ghost work. It's meant to help us call out work conditions where the value of the person providing that moment of service is literally erased. The most common ghost work tasks are often handling data entry. People might not be aware that most of artificial intelligence starts with gathering as much data produced by people just doing what they do every day online, and then from there taking those bits of data and making them as sensible to a computer program as possible. And it turns out it actually takes quite a bit of human effort to be able to create what's called training data for artificial intelligence. The downside for the workers is that this isn't work that is yet legally regulated or really recognized as a socially valuable job. And so they don't have the basic protections that come with doing a 9-to-5 office job. The paradox of automation's last mile is that as we strive to automate more so that we have less and less we have to work out on our own or hire a person to do for us, we're also going to open up all of these other places where we're going to demand more prediction, more automation. Like, yes, it's going to be cyclic. Yes, there will be jobs people no longer have to do. They won't have to attach keywords to the images of puppies, because finally computers can figure out what puppies look like. But guess what? Every time we come up with a new breed of dog, AI is going to be lost all over again. So just that is constantly producing all of these places where you need a moment of somebody's time and expertise. When we're looking at big data and the value of big data, the first question we should be asking ourselves is valuable to whom? Things will radically change if consumers see they have every right to say, you don't get my data without my permission. Meaningful permission, not a click of a terms of service agreement. That's not meaningful. Yet literally every single day, we are, without question, giving away our right to say, no, you don't get to have that. And in fact, we'll fine you if you take that. We have no way to go back now that we've built out so many systems that are data hungry and effectively solve problems through large stores of data. So we are able to do some really amazing things with large stores of data that people are producing online. How do we put people in the feedback loop so that we are able to say, hang on there, I see you would like to use data for this purpose. Let me check your permissions for using it for this purpose. I don't see that you have the permissions for that. Let's go back and find out if you could get them now. Rather than be put in this position of being told, well, we have your data, would you like us to use it for these other things too? That's not the right question. That's like taking somebody's wallet and handing them $5 and saying, you know, I took your wallet, but here's $5 to get home. That makes no sense. They genuinely just see data, and our job is to help them see people and human interactions so that they don't feel comfortable just taking what they can get.
People are generating this data, they're sharing this data, they're sharing, for example, their artworks. And the companies are having people label and classify that data. And once you have data sorted into categories, you have a sense of the kind of information that is in, say, a picture of a puppy. And this isn't just for images, of course. You can also use this to figure things out, like, is this person going to buy a toothbrush, or is this person going to respond to a specific type of advertisement? Once you have enough data, and enough data categories labeled with some degree of confidence, machine learning comes into play. We'll go deeper into how this works in a later class, but for now, we can think of machine learning as a tool that automates data analysis. It looks at 10,000 pictures labeled puppy or cat, it identifies which patterns tend to be present in the pixels of that image. And then it says, okay, that's a puppy. Much of this work is being done for the sake of image recognition, pattern recognition. Teaching an AI to see the world was helpful for all kinds of things. A car that drives on its own, for example, would need to recognize when something came into the road so it could stop. A vacuum cleaner might need to learn not to bump into stuff. Very basic AI, right? You could do that in the 1950s with lights, but we have cameras that maybe it could find some garbage on the floor and go for it, right? We're automating all kinds of things. And we already had massive data sets of images from scientists and researchers that would help things like identify species of plants and animals. But this is all very broad. And let's start talking about some specifics. One of these data sets that is probably the first to really be widely used is images of handwriting. So you can learn how to move information from a pen into digital text. Right? A company can learn how to move this information from a customer writing something to having that information in a document. And that's where the first real breakthrough with generating images happens. It's not much to look at, but this is an early example of a new idea. It's the idea that if you have a system that has enough data to recognize shapes and predict what they mean, then you can reverse that. And you can have enough data to generate shapes. Jan LeCun, an AI researcher, created image recognition software for handwriting in the 1990s. But here you can see some of the numbers actually being generated. This is a machine learning model that has identified patterns across lots and lots of samples of people writing down numbers. And it has learned that if someone is asking for a 0 or a 2 or a 4, then it's going to look like this. So there's some interest in this technology because it means that you can generate new data that already fits into the specific labels of interest to you. So let's jump ahead to 2013. Google has this massive image database. If you've ever gone to Google Images, you've seen it. And you could search that Google image database, right? So it needed to label and identify these images for search. And in that year, they finally arrived at a pretty reliable image recognition system, giving users the ability to upload an image and have a computer tag it instead of having a person tag it or the user tag it. Here you see the example that Google used to talk about this breakthrough. It's from their demo. It shows us that the system has identified a puppy, and it has identified a hat, and not just a hat, but a hat with a wide brim. Basically, the machine has seen enough images of hats and puppies by looking at massive data sets of hats and puppies, and every hat and puppy is read as pixel information. When certain arrangements of pixels are present, it says, okay, I think that's a hat. I think that's a puppy. We're going to go deeper into this later. The classifier has to look for patterns in the image based on what it's already seen. But it wasn't always clear how the system was identifying these things, which could lead to problems. For example, if you have a bunch of pictures of Arctic wolves and a bunch of pictures of dogs, how do you know if the system is recognizing the dog or the snow, right? If Arctic wolves are always pictured in being in snow, is the image recognition software recognizing the dog breed? Or is it recognizing that there's snow in this picture and therefore it must be an Arctic wolf? That's a hypothetical, but these are the types of questions that were abound in this time. On a personal note, I was in front of an image classifier in Australia in 2020 wearing a mask, and the image classifier said that I was a kookaburra because it could see this large beak. It misread my mask as a beak. So this is what we're dealing with, right? In 2015, Google engineers want to understand what the machine is seeing so they can fix or correct their pattern recognition models. Finally, they figure this out. They can design the system to infuse the patterns that it thinks it sees, right? And it can present it to them basically as a new image. And this ends up being very surreal. They call it deep dream, and it looks like this. Here on the left, you have an image of noise. This is just deliberate static noise. And to the right, you have the images that this model, trained to identify fruit, sees as potentially a banana. It's saying it's optimized with priors. You can think of that as given a particular data set that it's looking for. Priors in data science, a very simple translation of that just means you're starting assumptions. So what's happening is now we can see the starting assumptions of the image classifier looking for fruit and finding something like a fruit in this random noise. So the model is trained to find fruit in pictures. Traditionally, you hold up a picture of a banana, it says banana. You hold up a picture of an apple, it says apple. Here they're saying, we're just going to show you noise. Tell us where the bananas are, okay? Tell us how you make sense of this noise to see bananas. So what's the point of this? Well, in the next image, you could see strange associations in the model. So here's an image set trained on images of dumbbells, right, to lift weights. But it turns out the image set has been clumped together with arms holding the dumbbells with the dumbbells themselves. So you see these like weird arm things holding the dumbbells because so many of the pictures of dumbbells that it had been trained on included human arms holding them. Does that make sense? So when you ask this model to say, what are you seeing in noise? Show us kind of what you expect to see when you're looking for dumbbells. This is the way to do it. And you can see some of the weird stuff that it identifies. So if it had this thing of dumbbells where arms were in there, then who's to say that an arm holding a can of soup or something wouldn't be mistaken for a dumbbell? And they can go in and they can see that and they can make adjustments and they can think about what's in that data set. Now, almost as a goof, the engineers also decide, what if we give the system something that isn't noise? And they can see that the system will look at the image through that data that they are choosing, right? Bananas or dumbbells or whatever. And they can show them a picture and the model is going to give them a kind of hybrid of the two states. So let's look at what happens. On the left, you have a picture of a waterfall. And on the right, you have a picture of what the model thinks it sees in that picture. Deep Dream creates a lot of pictures of things that it has already seen and labeled based on the training data that Google had collected up to that point. So you see this waterfall over here, and then over on the right, you see these strange birds, right? You see these dog heads, strange fish sort of emerging. It's a bit hard to see, but you can see that it's finding these spaces and it's trying to make sense of them in a way that connects to the data that it has been trained to look for. Okay. The engineers also start taking the images that Deep Dream produces and they feed it back into the same model. So here you go. It sharpens these images, it strengthens these images, and it starts creating these really intense fractals. But if you look really closely, you see something a little disturbing, I don't know, weird. These are they have these textures like a lizard skin, they have animal eyes, they have snouts, and this is basically what Deep Dream does. Now, some artists get ambitious and they give us short films rendered through Deep Dream by taking every frame of a video and running it through the tool. So we're going to watch this video because it's AI-generated art, but we can also see how the image recognition system is making sense of the things in that image. So this is inside an artificial brain. It was created by Jonah Nordberg in 2015. And here, you start with noise. And it starts closing in and it starts drawing new pixels, right? So it's adding things that it thinks it sees. And now we're sort of moving into sort of fabric-y textures, right? And as it goes into these fabric-y textures, it's still looking for these abstract patterns, because this is the first level of how it's trying to recognize something. It's just trying to find basic shapes. And so it's creating this sort of hypnotic zooming effect. But it's looking for each shape that it would try to find than if it was analyzing an image. And here it's thinking, okay, maybe this is some fabric, right? These are some fabric textures, but then it's sort of saying, well, maybe it's not fabric textures, maybe it's just some light, some tiled textures, right? Okay, now it's saying it's finding textures in the textures. And it keeps going through, it's finding some sort of, I don't quite know what these are, right? I haven't looked at every data set that it has examples of. But the point is that these look abstract because they're taking the basic building blocks of images. Like 3 lines might indicate a wrinkle in a piece of clothing. But now I think we can all sort of start to see what's happening. It's found these circles. It's saying these circles look like eyes. It's saying if these circles are eyes, then what do these eyes belong to? And it's finding the patterns of eyes connected to animals. So here's, now it's taking a little detour into shells, right? But hold on, there's the eyes again, and there's the dogs again. And then you go in, you keep zooming in, and you start seeing eyes, and you start seeing dog heads, and then you start seeing eyes and dog faces and snouts, and eyes and dog faces and snouts. Then, maybe something else is in here? What's going on? Oh, nope, it's eyes, and it's dog faces, and it's snouts, and it's starting to see maybe ears, right? So it's going through, this is what it's done. Now, we're looking at this as a fractal, but if this were being an image recognition device, it might have just said, okay, this must be a dog, right? Dog, dog, dog. This is what it has learned to see. The eyes are changing. The eyes are starting to become a little person-like. They're starting to become less like a dog's, maybe more like a wolf's. But don't you worry, it's going to come back to dogs. It creates weird dogs because now it's starting to just try to think about what is the body of this head that is attached to the dog. What type of animal is this? And it's trying to figure that out by looking through this sort of pattern of bird imagery, right? Snake imagery, lizard imagery, maybe even people. So we can go through this and we can keep interpreting this, right? But I hope the idea that you're seeing, 2 takeaways. 1, Deep Dream 2015 was obsessed with dogs. There's some lizards. There's some bugs. There's some dog bugs. Okay? So it's identifying textures, and it's trying to make sense of these textures based on anything it can. And if it finds something, it's going to zoom in on that. It's going to amplify that until it can't figure out what it is anymore, and then it's going to try to connect that to something else that it sees, and it's going to try to render that. Okay. This is what we call bias. The machine has an internal bias to find something in these images and to show us how it sees them. And along the way, probably it's one of the first AI-generated image systems from this current batch of AI-generating image systems, because this really kicks off the whole image generation shift. So enough of that. In a few weeks, we're going to go deeper into what came next, what came after Deep Dream. And this is a class about contemporary AI tools. So the big ones are going to get a class each. We're going to go into GANs, we're going to go into diffusion, and we're also going to talk about machine learning. We'll do a kind of introductory high-level overview of machine learning and what all that means. But I wanted to finish today, the third section of our talk today, with another way of thinking about data. We talk a lot about data, and I think it's become a kind of meaningless term, right? Thinking about how the images that we got out of Deep Dream were completely shaped by the images that Google had already collected and classified. Deep Dream knew a lot about a small set of images, because if you wanted an image classification system for fruit, you had to go out and collect the data of pictures of fruit for that system. And once you had enough, automatic classification would come, but you were picking categories to train. So when we were looking through that fractal, we're looking at categories that had been selected by Google to train libraries on. Dogs, mostly dogs, fish, lizards, right? Fabrics, this kind of stuff. So I want us to think about how data sets are constructed, what they include and leave out, and how they shape the things that they are measuring. And when we are thinking about the data used in today's image generation, it's important to think about this stuff for a lot of reasons. But to start us off, I want to talk about color. Colors are created by nature, first and foremost, but humans are the ones organizing and naming those colors. That involves human decisions. And you may not think about it, but it also involves technological influences and economic interests. And this stuff reflects how data sets are being assembled and distributed today. And there's a hardening of certain subjectivities that comes to describe our world when we turn it into data. And we'll see what that means in this part of the lecture. For now, in this image, you see a simulation of the same bird, painted according to the colors of inks that were available to printers in 1814 on the bottom and 1886 on the top. Now, this is not precise. The colors of ink, the colors of screens, this kind of stuff, consider this a simulation. This is a thought experiment, though it is true that certain colors were unavailable to printers in 1814 and 1886. It's just these precise colors are not necessarily the ones that they were. So imagine you're looking at this image in 1814, and you're trying to understand what a bird looks like that you haven't seen. It might be really hard to look at a bird from this picture in 1814 and figure out that it is a bluebird, right? In 1886, the picture becomes clearer. That's because certain colors, and blue was one of them, became cheaper and easier to reproduce between 1814 and 1886. So information became more detailed. And before color photography, colors had to be described through this error-prone format, the written word. If you wanted to describe a color to someone through a written letter, you had to use words. So imagine trying to describe the color blue to someone who had never seen the color blue. You would have to liken it to something that they may have seen, right? And that's exactly what ends up happening. In 1812, the mineralogist Abraham Werner puts together a book called Nomenclature of Colors. And this names the colors that he observes in rocks. He's a mineralogist. He's interested in minerals. So later, this book was illustrated and republished with color patches by an Edinburgh flower painter named Patrick Syme. And this is a version of that. So each of these books would have been hand painted by this painter to match the color that's being described. And this wasn't the first book about color, but it was a pretty influential early reference. Werner's color system came from minerals, so his standard color system was based on the colors of 79 known minerals, which later was extended to 110 as he started adding other natural phenomena into this book, including birds and things like this. It also introduced hierarchies because he was organizing these colors. So he originally decided that orange was not its own color category, but was a subcategory of yellow. He decided that purple was a subcategory of blue, and these kinds of things. So he was making decisions about organizing color. He also chose purple not to be its own color because it was simply expensive. Purple dyes were the most expensive to produce and obtain at the time. So you can see the structure of how this worked. You could recreate this in Excel today. This is over 200 years, but information is organized in grids, right? A series of columns and rows with a number on the right that references the row that you're in, and the color was named. So you have the name of the color there, and then you have the color itself represented, and then you have a sample of it. Next to the sample of it, you have the names of an animal bearing a similar color in its plumage or its fur. Then you have a vegetable or fruit, and then you have the mineral. Some categories have all this information, some are missing information in this space, right? Maybe there's not a bird that is greenish blue. So there's information missing as well. But what's happening here is that Werner is putting together a data set, and the goal was to establish a reliable common reference that left less to the subjective imagination than the written word. Werner wrote that the written word was defective, that description was defective if you had to be ambiguous, and they needed regular data to refer to, so you needed something to reference, and that's what this book was doing. So he essentially was creating a standard for color. This book of data and the standardization of color names was only useful if it was widely referenced, and in that regard it was a success. The book was intended for mineralogists, but even Charles Darwin used it to describe the colors of birds and mammals and the skies around Galapagos as he was writing about his discoveries on evolution in The Origin of the Species. Some examples that Darwin pulled from his book include hyacinth red and chestnut brown being used to describe a cuttlefish. So that's strange, right? Hyacinths are flowers, chestnuts are, chestnuts. Why would you use these words to describe a fish? Well, for the same reason you would describe a slug as primrose yellow, right? The color of a flower. Or you describe a type of coral as a light purple. And what he was doing is he was referencing the natural phenomenon he was seeing to this book. The book emerged as a standard reference for color, though by no means was it an objective or exhausting list of colors. Werner and Syme would convince everyone to see the world in their personally selected shades, what was useful in identifying minerals and a handful of plants. So this was the initial constraint. The work was further constrained by what could be reproduced with available paints. I mentioned this before. If you're thinking the data is accurate, something that I like to think about is that if you look at a crow's wings in the sunshine, it's not actually black. It's purple. It's streaked with purple. And if you're in a world where purple paint is too expensive, then you might be tempted to say, well, a crow is black, actually. And it's interesting to consider that maybe we would see a crow very differently if someone put a crow in here as purple and it became standardized, right, as sort of this widespread understanding. And a lot of this stuff is cultural too. Certain cultures will see green and the color of the sea and the color of the sky as all one sort of bluish green shade, right? So there's a cultural influence in how we interpret color as well. But my point here is that colors have been lifted from the natural world, standardized into a world of language and symbols through this book. And to be understood, you had to make mental connections between the observation of the colors or minerals in the world that you were looking at, and you had to reference the closest representation in this color dictionary. Does that sound familiar? I hope it does. Because what we're describing is, in a sense, the way that computer imaging technology has to make a reference to a data collection in order to make sense of that world, in order to describe that world. So just like someone would have to look, Charles Darwin would have to look at this book to describe a cuttlefish as a hyacinth, image recognition model would have to look at a data set of dumbbells to describe a dumbbell. And that data set is whatever's in that data set. And this colors were whatever is in the color book. Okay? So I hope this connection is starting to make sense. Now, this is a great way for expanding the way we communicate. Just like an AI model, it helps us have more accurate understandings of new things because we can relate them to pre-existing things. AI isn't so good at that. And in the process of deferring to AI for this stuff, we lose something. We lose the gradients and the shades of the world that don't fit into its dictionaries, the way that we might lose the colors and shades that don't fit into this color dictionary. So if you had to imagine birds aided by an illustration with a reference only to the colors of rocks, it would be a different bird than the one that you would use to describe with 1,115 colors, right? Which came about later on in another book that was used to describe birds. And our world and some birds are more complex and vibrant than can be communicated through a simple dictionary. Colors became a data set. Someone collected examples, put these examples together, and then institutionalized their names. The colors in that book were constrained by the technologies available at the time. Purple was expensive, so they didn't focus on it. The colors were assembled by people with a specific field of expertise, so all the colors were named after minerals. Nothing wrong with that, but it's there. And then they distributed this data set as a book that other people could use, and those people used this data to talk about their discoveries, and this information started becoming perpetuated. I wanted to talk about the history of color because today, data really doesn't work any differently. We talk about it differently. Today, we might say that a machine did something, or an algorithm did something, or the artificial intelligence decided. But in fact, people designed those machines. People decided what data to use. They decided how to collect that data, and they decided what the machine was going to decide. I would say that whoever collects this data has an enormous power and responsibility over how to shape the way that this data is shared, used, interpreted, and understood. So we're going to look in this class at data from that perspective. Right now, as many of you know, there's a big scandal around how the data sets used for AI tools were collected and who they were collected from. There's also a lot of questions around this data about who's not in it, and we'll dive deeper into that too. It's very possible that these decisions, like the way we named colors, are going to be with us for a very long time. So I wanted to talk about them and just think about how we can understand them and make sense of them. When we talk about today's AI, we're really talking about data. And it's important to remember that data is carved out of the world by someone for some purpose with some limits. Data simplifies and reduces the world, which can be essential for communication. But what we observe and communicate should really never be confused for what's true and real. Data of any kind, by definition, shrinks the world to discrete points on a chart or a computer, or in an AI-generated image or text. Color dictionaries were designed to create a shared reference between the author's observations of the world and people who couldn't see that world. People in England who couldn't see a bird that was in North America. That's something that data scientists and engineers can learn from the experience of designers and artists, to think clearly about the information that's being collected, to show people how it was collected, and to think carefully about the tools that you're using to reproduce that data and the choices you make about what to include or leave out. As artists, or as data scientists, and you're going to be somewhere in between the two as an AI-generated artist, these are the things you can come to and think through with real intention, real choice, and to do that, it's important to understand their context. So next week, we're going to talk deeper about some of these ideas and questions, and I'm excited to see you then. Thanks so much.